What I want to talk about today, as Sibyl said, I work on gravitational wave astronomy, and in particular, I work on looking or searching for mergers of compact objects that can produce these gravitational waves. And I wanted to talk to you about work that I've been doing since I got here. So in searching for compact mergers that are of high mass, and I will explain what's high mass and why these are interesting. And what I'm going to talk about, I summarize in this paper. So 2 from the last year, 1 that we posted in the archive on Monday, and 2 that should be coming in next week and probably the next one. So as a summary of what I'm going to be talking about, since not everyone here is too familiar with gravitational waves, I will provide a brief introduction to what compact binary mergers are and how the gravitational waves these produce look like. Then I will give a brief intuitive summary of the main tool that I personally use when I work with all of this analysis, which is that of Bayesian inference, which is what we use to guess the properties of the sources behind the gravitational waves we observe. And then I will focus on the case of high mass compact mergers, because these are very, very challenging. So I want to discuss a bit the kind of problems or challenges we face. And I will give some examples of why these are actually very profitable, despite how challenging they are. So you can get a lot of science done with these binaries if you're able to detect them, which is tough, and to interpret them. So then I will focus on a concrete example of a high mass merger, which is that of GW190521, which is a gravitational wave we observed in 2019, and that has been really followed up by many studies providing many different interpretations of this event. So we'll discuss the sort of original, or call it canonical, version that we provided within LIGO and Virgo. And then I will go a bit to the alternative scenarios that have been discussed for this wave. And in particular, I will end up talking about the possibility that this merger can be interpreted as a merger of 2 new compact objects that as of now are just theoretical objects called boson stars, and in particular, a certain type of boson star called a Proca star. And then once I discuss this GW190521 event, I will go through the analysis of 3 more events that have been reported by LIGO and Virgo, 2 confirmed or labeled as detections, 1 not yet. And then if I manage to get there with time enough, I will discuss some techniques we are now trying to implement to enhance our sensitivity to these high mass mergers. And in particular, how can we exploit what we call higher gravitational wave emission modes to detect these high mass mergers. So gravitational waves, LIGO-Virgo, and a bit of current detections. So I guess I don't need to go to the introduction of what a gravitational wave is. A gravitational wave is a perturbation on space-time that propagates away from the source at the speed of light, and it carries information about the source that produced it. Because these waves can travel basically unaltered through the universe, the wave we get really can inform us about what produced it, and we can study those to study really violent events in the universe. So there are many sources that can produce these gravitational waves. Each one has a characteristic gravitational wave frequency, except for the cosmic microwave background, we could basically extend through all frequencies. And the main source I work with are compact binaries, as I said, and these are collisions of compact objects. For instance, black holes, neutron stars, or other exotic objects that could be around there, like boson stars or quark stars or whatever you can imagine. There are other sources that people are trying to detect, like core collapse supernovae, extreme mass ratio in spirals, in which you have like a supermassive black hole and a tiny object, typically a tiny black hole that blocks into it. Spinning neutron stars that can generate continuous waves via deformations on its surface as they rotate. And of course, supermassive black hole binaries that will be searched for by the space detector LISA when it's launching around 2034. So for now, despite the fact that there are some detectors planned in the future, we need to attach to what we have right now, which are the LIGO and Virgo detectors in the US and in Italy. And these are most sensitive to the signal emitted by black hole mergers, neutron star mergers, because of their characteristic frequency. So to visualize the kind of event I work with, let's look at this simulation from the folks of the Max Planck Institute. So these are two compact objects, say two black holes, that are going to spiral around each other and then merge as they produce gravitational waves. So the two objects are orbiting around each other. Because they orbit, they miss energy in gravitational waves. That releases energy from the system. Therefore, the gravitation starts to win the battle. And these two things approach each other. The orbit gets faster and faster. The gravitational wave emission gets stronger and stronger because the gravitational field is stronger. And at the end, we have the fusion of the two objects that produces a very vast emission of gravitational waves. And at the end, we're left with a distorted black hole that's going to release the distortions on the event horizon via ring-down radiation. I will discuss a bit about this ring-down radiation in a couple of slides because it's very, very interesting. So where do we stand in terms of gravitational wave detections? As I said, we have, as of now, 3 active detectors, 2 advanced LIGO detectors in Hanford and Livingston in the US, 1 Virgo detector in Pisa, Italy. And we have now a 4th detector that will be joining LIGO and Virgo for the 4th observing run, which is Kagra in Japan. The first detection of gravitational waves happened in 2015. So this super famous event called GW1514. For those that haven't noticed yet, year, month, day. And as of now, depending on whether you believe all of the gravitational wave events we report are real signals, we stand at around 90 gravitational waves observed since then, which is not a bad pace.
What happens if you get 2 signals the same day?
We have got 2 signals in the same day. So what you add is a underscore, and then you describe the hour, minute, second. So we are now we were a few months back facing the problem of how to name these things. So luckily enough, I'm not going to be talking about any 2 events within the same day, so I can attach to this rather simple naming. So this is a kind of summary of the 90, not the 90, sorry, these are the first 50 observations we have. And the whole message I want to give here is that this basically come in 3 flavors. We have things that are consistent with a merger of black holes. We basically know that these are black holes because of the masses. We have those that are consistent with binary neutron stars. And again, we can know these are binary neutron stars only if we observe an electromagnetic counterpart. Otherwise, we kind of need to guess it because of the masses. And then we have a couple of events that are consistent with mixed mergers of black hole neutron star. And with these events, we can, let me go back. With these events, we can retrieve a lot of information, not only about the properties of these events, but then we can go ahead and do population studies. We can do cosmology. We can try to guess, given the masses that we observe, whether there are some gaps in the masses of the black hole population. And therefore, that tells us things about how stars evolve and die to produce those black holes. We can do population studies that let us understand the properties of the environments in which these things are forming. Are they dense? Are they less dense? We can study the formation rate of black holes through the history of the universe. And of course, we can do cosmology. If we get, the most simple thing to guess is if we get gravitational waves from the one side, light from the other, we can compute redshift, distance, and therefore try to study the Hubble constant or try to extract the value. So let's go about how do we try to infer the parameters of these things. So this is an example of a typical gravitational wave that we observe. And I say typical because most of them look like this. And look like this means that you can basically identify 3 parts, or at least 2. The first one is the in-spiral process that I was discussing at the beginning. So you have the 2 objects orbiting around each other and at small velocities compared to that of light. Then we have the merger. As the 2 black holes smash into each other, you have this burst of gravitational waves. That is, if you have a massive system, this is going to be, the frequency of this thing is going to be in the sweet spot of our detectors, or is most visible. That's why these systems are going to be very convenient. And at the end, we are left with this distorted black hole that is going to settle to its final shape, emitting what we call ring-down radiation, which is this exponentially decaying emission of rather constant frequency. This is very useful because this allows us, in principle, to identify in an isolated way what the properties of the final black hole are, and then compare with our expectations from the spiral. If you look at this wave in terms of time and frequency, what you see is a frequency that slowly evolves towards higher frequencies, which is basically what you see here in the evolution of the separation of these crests. And then as things go towards merger, you see how the frequency ramps up, as well as the amplitude, which is given by the darkness or the yellowness of the color. And at the end, the signal just dies. So this is what we typically call a chirp.
So the merger is the same for a black hole and for neutron stars?
For a couple of neutron stars, what you would see is a merger and then some post-merger signal.
Well, but post-merger is very difficult to see, but the merger is the highest. So it's the So is there no way to tell one from the other?
You could tell the difference basically in the merger stage and prior to the merger stage when the two stars are very, very nearby or very close, because you would start to see the effects of the tidal disruption.
Yeah.
So in that case, you could tell the difference apart, but with the loudness of the signals we have right now, we cannot observe such a detail. Actually, I don't have on the top of my head what kind of loudness you need to observe the tidal deformability. Maybe someone in the room knows it. But, so how do we guess the properties of these things? So this is my little introduction to Bayesian inference. So we start with some data that comes from our detector. And given this data, what we do is we want to compare to a bunch of models we have for this data that depend on some source parameters, masses, spins, inclinations, equation of state for neutron stars, distance, you name it. The way we try to guess which of these models represents best, or what family of these models are consistent with this signal, are given by the following ingredients or formula, which I will try to describe in an intuitive way. This, you have in the one side the likelihood. Note that here is the only place where the data comes in. So this term is basically telling you how similar the data is to your model. So this is what you would do intuitively. Then you have your priors, which is your prior belief on the existence of these parameters in nature. And that's it. You multiply those two numbers, and then you get a posterior probability for the source parameters. For those that are not familiar with Bayesian inference or statistics, the effect of the prior, I always give the same stupid example, is imagine these are not gravitational waves. Imagine I send you just to a zoo and I give you a bunch of animal cards. So in each card you have an animal, which is one of these waveform templates. And then you get to a moment where you have some data, so you see some image. And this image corresponds to something that looks like a blurry head with a kind of a horn. And then you say, okay, I have two templates that give me a high likelihood here, a unicorn and a rhino, okay? And then your common sense prior tells you, well, in this universe or in this earth, I think that unicorns do not really exist. So then your posterior probability is gonna push you to the rhino, not the unicorn. So this is how this business works. The thing is that if the data is not too very informative, all of your inference or most of your inference may be coming from your prior assumptions, and you may be missing unicorns, even if you have them in front of your face. So that's a huge challenge, or is one of the challenges when we have at our hands high mass events, for which I will talk about this later. We only see this later part of the signal. So on top of inferring the parameters of the signal according to some signal model, we may also want to decide which signal model is describing our data best. So for instance, the main scenario I'm going to be talking about, we may be using those waveform templates that I showed for black hole mergers, or for some alternative scenario like boson star mergers. And in this case, you want to decide which of the two works best. So as I said, in each of the two cases, you're going to be comparing the signal with each of the two models. And how do you do this? So I need to go back to this seed that I showed in this formula, which, if you don't care about model selection, it's just a normalization factor. When you integrate your probability across all of your options, it needs to give 1, because otherwise it's not a probability. And so you normalize all of your probabilities by that. But when it comes to selecting models, this seed is what determines which model you prefer. And this is the case because intuitively what this seed is computing is the average likelihood or the average fit that you obtain to the data with your signals. So how does this work? In which cases will you obtain a large evidence for a model or the other? You will obtain a large evidence primarily if your model is able to fit the data. If within your model you find templates that fit the data very, very well. Now, you cannot do this at the cost of increasing massively the amount of options you have in your model, so your parameter space, folding in or bringing in very, very useless waveforms. In this case, are not going to give a good fit to the data. This is the mathematical realization of the Occam factor, or the Occam penalty, that you study in philosophy. I mean, you will prefer the simplest model that can give you the best fit. And things will depend a bit on how you choose your priors, but that's a kind of different story here. What am I doing here? Okay. So let's discuss a bit what we get from a typical LIGO-Virgo event. We have a longing spiral, and this means that we're going to get a lot of information from here. And this information is going to allow us to constrain the parameters of the two bodies that are in the spiral. And that's an advantage to infer the merger, because general relativity tells us what the final object should be. So in reality, most of your information about the final object is going to be coming from here. However, when you are in the opposite case, where you have a thing that is very, very massive, and therefore you don't see any of this, as I will show later an example, your inference is kind of going the opposite way. You're looking at the final black hole, and may not be a very loud signal. And then when you try to infer the parameters of the two bodies that in spiral or merge to produce this final object, you're going to be essentially saying, well, I know the final parameters, and therefore, let's see all of the binaries. Let's see what are the binaries that can give me that final black hole. Those will be more or less equally likely, and then you will select things based on your prior assumptions. Okay, so as I said, this is the typical signal we observe in LIGO-Virgo. And this means that we know pretty well what model to use to fit these things. We found that the typical model that we use, that is two black holes spiraling into each other in a circular way without eccentricity, is a pretty safe assumption to analyze all of this, because we get a lot of information of the in-spiral dynamics. And in fact, there have been searches for deviations from this circularity in LIGO-Virgo events, namely searches for eccentricity in the system. And for most of the events, the bounds that we have placed are pretty tight. So the eccentricity, for those that do not know, basically goes from 0 when it's circular to 1 when you have a head-on smash. And you can see that these bounds are all below 0.05. And by the way, all of those are consistent with 0. There are a few exceptions to that, but they are very recent. I will not really get into them. So let me now get to the event or the signal with which I've been working for the last 2 years, basically. You see that this looks nothing like what I showed before. This is a very short signal. You see what looks like a merger, and you don't see anything before it. So you don't see the in-spiral process. As I said, this can happen because of one reason. The event is too massive, and therefore the frequency of the in-spiral signal is too low to be observed by our detectors. And option 2 is that maybe there is no in-spiral here. This could just be smashing of two objects without an in-spiral process, and therefore you're left with this. Just to see, or just to show you how this looks in terms of time frequency, you can see that I don't have the initial part of this supposed chirp that I should be observing here. So again, all of my inference about what happened in here is basically going to be driven by condition 1, whatever it happened needs to produce this black hole. Condition 2, I let my prior assumptions choose. So as you might be guessing already, detecting and studying these high mass mergers, for which you basically see something like this, is very challenging, but it's very profitable if you can start to observe these signals in a systematic way and understand how to figure out what caused them. So the first thing is that you have strong field gravity at its best.
Sorry, what is the estimated final mass?
For this thing is 150 solar masses in the source frame. But that source frame estimate depends a bit on your model, because depending on your model, your signal is going to be louder or weaker, and therefore you will have one redshift or the other. So that's going to condition your mass estimate. I'm going to get to that, but 150, above 100 is the relevant number, actually. So what I mean by strong gravity at its best is that for this type of signal, the emission coming from the collision of the two objects, so from the merger part of the signal, is actually falling, has a frequency such that our detectors are most sensitive to that. If you reduce a lot the mass, then the signal is going to start to have a higher and higher frequency and escape out of our sensitivity band. But for signals like this, that's where we really can observe the dynamics of those horizons. When the two objects are about to collide, we in principle expect that the source will start to emit not only through the main gravitational wave emission channel, but also through subdominant channels that are called higher harmonics. These higher harmonics are basically a reflection of the complex geometry that the final black hole acquires, and it can drive very, very funny signals that actually are telling you about what's going on with those horizons that are colliding and with the final one. So here I have an example of one of those signals from a rather unequal mass object, or unequal mass merger. What you see here is the signal emitted as the black hole has just formed and is relaxing to its final shape. And you can see that this kind of time frequency map deviates a lot from the one I showed, which was just a single chirp. Here you can see the frequency going up and down, and I'm not going to get into that, but this tells you about the shape of that final black hole. Since you are able to observe several gravitational wave modes,
so
and
that was real data or a simulation?
This is a simulation, but it's a numerical simulation. So we actually are searching for this right now. The problem with these things is that they are emitted basically from the orbital plane. So you need to be at the orbital plane of the collision to observe it. And the signal emitted in that direction is much weaker. So you need the source much closer, and your options of detecting it kind of go down. So since you observe the moment of the collision and the posterior ring down of the final object for these high mass mergers, and you in principle can observe many gravitational wave emission modes, you can do studies you can test general relativity. So one of the examples of the things you can study or check is the so-called no-hair theorem, which is a mathematical statement. It's a statement about the complexity or simplicity of black holes. It's basically telling you that black holes are labeled by three numbers. You know three numbers, you know everything: mass, spin, charge, in practice, mass and spin. And you can actually test this by trying to find several emission modes that are emitted in this ring down. This ring down is not just a single damped sinusoid, it's a combination of many of them. And you can check the cross consistency of these modes, namely the no-hair theorem basically is telling you that the damping time and the frequency of all of these modes that are emitted here are only given by the mass and the spin. So if you detect one and you infer the mass and the spin from one, you can infer what the other mode should look like. And people have been trying to do this, and actually there is a claim of a measurement of two such ring down modes in the merger of our first detection. And well, the data is weak enough so that it's impossible to constrain things very much, but they are consistent with the expectations of general relativity. I see that Lola is trying to figure out what's here. So basically what this is plotting is the deviations in the frequency and damping time of the secondary mode with respect to what you expect. So you would like these things to peak at 0, and well, they are consistent with 0. Let's leave it at that. And when you can observe these final mergers, you can also have access to strong field phenomena like gravitational wave recoils, which is a thing I'm very interested in. Gravitational wave recoil happens when after the merger, the final black hole gets ejected at a given recoil velocity. This is because the emission is asymmetric, so you need to conserve linear momentum. These kicks are very relevant in astrophysics because they can get to values of thousands of kilometers per second. And such values are enough to basically eject the remnant out of any environment and then prevent it from undergoing subsequent mergers, and therefore create hierarchical formation, black hole formation channels. Since the objects involved in these mergers are going to be, by definition, very massive, they may have masses that in principle we do not expect to see for black holes. And this is because the main channel for black hole formation is the collapse of stars through supernovae. And we know that there is a process called the pairing stability supernovae that basically prevents black hole formation in the range of 65 and 120 solar masses. So if you observe one of those, then you can start to make or to test the idea that this black hole should be the product of a previous merger, and therefore that's going to tell you about the properties of that environment, because that environment needed to retain the black holes formed after those mergers. And since these things, when they are, if you find that a black hole is a second generation black hole, these things, these hierarchical formation channels may mostly happen in very dense environments. For instance, active galactic nuclei. And in that case, the black holes that form when they recoil are going to emit a flare, or can emit a flare that you can use to measure the redshift to the source. And then you can do cosmology and try to measure things like the Hubble constant and all of that. But these things are very challenging to detect. First, because of their morphological properties, they're very short, so they can be very easily easily mimicked. Oh my God. By things like this, which are glitches that populate our data. So if we have signals like this that are actually morphologically identical to glitches, to noise artifacts, it's very difficult to tell them apart, and that difficults the detection a lot. Now, as I said, also these signals from high mass mergers can contain higher harmonics that basically become apparent in the merger. But the searches we use to look for black hole mergers neglect these higher harmonics that give you this kind of complex morphology at the end. So our searches are very, very inefficient at detecting this. And as I said, the interpretation, assuming you detect one, is very difficult because you only see the merger. So you don't have information about what happened before. Because we are in the merger ring down regime, we really need numerical relativity, not analytical calculations, to obtain templates for this kind of merger. So these things are kind of exploiting our capacity to predict the signals. And as I said, whatever result we get anyway is going to be really influenced by the project. So let me go about what we said within LIGO and Virgo about this GW19521 signal. So if you assume that what happened here was a circular merger that then produced this, you can just analyze the event with the corresponding templates and try to infer some properties. So the first conclusion is that the remnant is an intermediate mass black hole. So this is a posterior distribution for the two masses in the source frame. So the first one is around 80 something solar masses, the other one is around 60 something solar masses, but the nice thing is that the total mass is way above 100, not way above, but above 100. So that you can basically say that the remnant is above 100 solar masses. This places it in a range that is called the intermediate mass black hole range. These things, these kind of optics are very important because, first of all, we haven't seen anything between 100 and 10 to the 5 solar masses to date. And therefore, it's very difficult to explain how a population of black holes of 30, 50, and so on solar masses can actually give rise to the supermassive black holes that we see in the center of the galaxies. So finding these type of things and actually see them forming actually is a clue towards the fact that this may be formed through hierarchical scenarios in which you just see subsequent black hole mergers. And then, as I said, the primary, no, I didn't say it, but you may have guessed it. The primary black hole is sitting perfectly what we call the peri-instability supernova gap. So it should not have formed through stellar collapse. So this is basically telling you that either, as I would like to think, this is not a black hole at all, or this has been formed through hierarchical formation channels. And another interesting thing is that despite the fact that I told you that there is no in-spiral in here, actually there is. I mean, the merger, according to our waveform models, let's say, starts here. So there is enough information in here to say that if you assume this is circular, you need orbital precession to be able to reproduce the signal. And you may say, where the hell is that coming from in such a short signal? And I can tell you it's because of how fast this signal is ramping up. If you want the signal to ramp up this fast, you cannot just do a non-precessing orbit. But it turns out that for such high mass systems for which the signal is so short, you can actually mistake precession by orbital eccentricity. Both can give you the same effect. An example is here. We considered a reference signal, which is just an extreme eccentricity case, a head-on collision. So you only see the merger emission. You don't see any power at lower frequencies coming from any spiral. This is the best you can do to fit this with aligned spin, so with non-precessing black holes. So you cannot really fit the data, but with precession, you actually can. And this is because the precession of the orbital plane is modulating the amplitude up and down, and it happens in this case to kill the emission just before the merger. So you can just confuse these two things.
30 minutes.
30 minutes, okay. So this has raised many interpretations or many possible faces to this event. So the first one, LIGO-Virgo, circular precessing. Then this can be confused with eccentricity. So therefore, there have been people that have actually tried to reproduce this event with actual eccentricity, and they've seen that things look consistent. Also, there have been reanalysis of what happens if we choose a prior on our masses that actually removes the peri-instability supernova gap. You can obtain some result that actually tells you, well, you may not be populating the peri-instability supernova gap, but I would not give too much. So the problem is that you may choose whatever priors you want, but you also need to feed the data. And these people is not able to feed the data. So there is people that have been also compared the signal with simulations, with numerical simulations that have eccentricity and precession. Those happen to feed the data quite well. And as I'm going to be talking about, we actually went a bit more nuts and said, what if this is a head-on collision, not of actual black holes, but of boson stars? So yeah, let's go about that. So what are boson stars? So there are people that is way more expert in boson stars than me, because I don't really work with them. I work at the data analysis side, but let me try to explain what a boson star is. So this is basically a Bose-Einstein condensate of ultralight boson fields. And in practice, these are compact objects, just as black holes, but that do not have even horizon, and they don't have a singularity in the center. So these are called usually black hole mimickers because they can basically reproduce the gravitational effects of black holes, both in terms of the gravitational wave emission and in terms of their electromagnetic effects, in terms of light bending and so on and so forth. The interesting aspects for us, or the interesting aspect for us, is that this can have spins larger than 1 because there is no even horizon and no singularity that can pop out of that even horizon. This is very interesting for us because we were actually trying to compare the 1905-21 signal to head-on collisions of black holes. If you do that, you find you cannot really reproduce the data because there is not enough angular momentum in the system to give you the spin of the final black hole, because you're lacking all of the orbital angular momentum of the orbit. However, if you can spin the individual objects a lot, then you get that angular momentum contribution to the final object. So this is why we actually try this, and also because we don't know how to simulate in a computer things that are not head-on collisions of boson stars. We are limited now by that paradigm.
So you're saying, I mean, the exterior metric is Kerr with A larger than 1?
I guess that large.
So
it's a compact object that can have a angular momentum over mass squared larger than 1. And at the end of the process, you form a black hole.
But the argument you gave was that there's a horizon, or what was that?
Oh, for Praga stars, for boson stars, there is no even horizon.
Yeah.
So at the end of the process, at the end of the merger, you form a black hole.
Yeah, but then you would mean that to form a black hole, it should slow down somehow.
Yes, because you will slow down basically because at the end of the process, you're emitting angular momentum away. And at the end, you form an object that is so dense that it collapses to a black hole. And yes, I mean, basically you radiate a lot of your angular momentum in order to be able to produce a black hole. So we can get highly spinning remnant black holes from a head-on collision. So these things share all of the properties so boson star mergers are going to have all of the same parameters as a black hole merger: masses, spins, inclination, distance, whatever. But there are going to be specific parameters to the boson stars that describe the new physics that you have in there. The first one is the oscillation of the ultralight field. And this basically determines how compact the star is, so how similar to a black hole those stars are. And then is the mass of the particle that is forming up the star, which once you have the frequency, it tells you the maximal mass this can have before collapsing to a black hole. And this is important because we want the remnant that is forming to be massive enough to collapse to a black hole and bring down, because otherwise there is no way to reproduce the LIGO-Virgo signal. And these are very interesting because, I mean, ultralight bosons, as some of you may know, are very good candidates to account for part of the dark matter content of the universe. Yeah.
So they account for the majority of dark matter. Is that in the form of all of these boson stars just floating around the galaxy, or any other galaxy?
Ultralight bosons can form these halos, yeah, dark matter halos in principle, and they may account for.
How big are the halos?
I don't know.
Yeah, I mean, what I'm wondering about is there's a maximum. If you know the mass of the boson, there is a maximum size of whatever structure.
Oh yeah.
So then, the question is the structure as large as the galaxy, or is it just as large as the large?
In this case, if I guess that if the ultralight boson has the mass we're inferring, it's not going to be the size of a galaxy, because we are talking about objects that are the size of these things, which is right. So not that different from black hole. A lot of those things. Yeah, but that's why one says part of.
Sure.
Okay, so there is a whole Pokemon zoo of possible ultralight bosons. They can come in many flavors: scalar, vector, tensor. You can have real or complex fields. And the important thing about this is the kind of structures that you can get out of these fields. So in particular, when I put this symbol, it seems basic. It means that these bosons can basically form two types of structures that are relevant for me. The first one are ultralight boson clouds. And these clouds are relevant because they can actually contain or can form around black holes. They will interact with them through triggering super-radiant instability, and they are going to pull spin away, angular momentum away from the black hole. So they're going to slow them down. So a technique to look for signatures of these clouds is to find or to try to see if the black holes that we observe have a cap, are capped in their spin. Also, this super-radiant instability is going to produce a continuous gravitational wave emission from those black holes that in principle should be observable by our detectors. However, searches for such clouds have not yet been successful. So let's go for the case of stars. You can form stars out of scalar vectors, but these stars are unstable when they rotate. So that's not very interesting for us. So in order to obtain stable rotating stars, we need to attach to the vector boson case, which is also called the Proca field or the Proca boson. So just to remind you how the things we look for are or look like, this is the typical signal from a compact or from a black hole merger. You have the spiral, the merger, and the ring down, and at the end, the final black hole. But for the case of a boson star collision, the thing changes a bit. It looks more like a neutron star collision. So you start with the two stars. When the two merge, you have a hypermassive boson star, and then depending on the properties of this hypermassive boson star, or let's say the compactness, this star will survive for a given amount of time before imploding into a black hole. So if it's not too compact, meaning, as you kind of said, if it's spinning very high, if it spins very high, it will survive for longer and emit these characteristic pulses, and at the end collapse into a black hole, provided it's compact enough. If this is already very compact when it forms, then the thing survives for very short, and then it implodes to a black hole automatically. And this is the case we're going to be working with because we want to reproduce the 1905-21 signal. But actually, if you want to find a smoking gun for the existence of boson stars, you would need to look for these things, I would argue. So the people in Valencia and Aveiro have been working or simulating these mergers of boson stars for boson stars with different properties. And initially, the first study we did, we attached to the equal mass case, just varying at the same time the frequency of the two stars or the compactness of the two stars. So we can compare these things to the data. This is just a video showing how the waveform or the signal emitted is varying as a function when we vary the frequency of the two stars that are colliding. Nothing really important to report, but that you don't see any glitch or any non-smooth variation of the signal, so things look good. And then we can compare our signals or our waveforms labeled by the two frequency oscillations. There are things are those messages in Zoom?
Your email, I think.
Oh, shit. Okay, sorry. So this is our current simulation bank, labeled by the frequencies of the two stars. You can also think of this as a varying the mass ratio of the two stars. So this is our initial study. As I said, we attach to this family of simulations, all of them equal mass with the two frequencies varying at the same time, and then we extend it to the case of the other. So all of these students from Hong Kong and India help a lot in doing this analysis, and this is the conclusions we obtained. So for our initial equal mass model, we obtained masses that are actually higher than those of LIGO. And this is because we obtain a luminosity distance that is 10 times shorter than the one LIGO obtains. But this makes sense. This is no problem. The problem here, the thing here is that we are doing a head-on collision. A head-on collision is much weaker than a circular one in which the two things have time to accelerate. And therefore, you need to place it way closer to be able to get the same signal. That reduces your redshift. And your redshift reduces your estimation increases your estimation of the source frame total mass. The estimate for the final spin coincides or is consistent with that of LIGO. And I'm gonna jump directly to the new physics parameters or the characteristic parameters of the boson star, which is what we really were after. So we can measure the oscillation field of the two stars pretty well, or we can at least find the whole posterior. And from that, we can infer a mass, combining this with the total mass, that is about 9 × 10⁻³ electron volts. So this is really an ultralight boson. And the funny thing, to me, the most interesting thing is that you exclude 0. Now, this cannot be taken as a golden plated number or anything like that, because here we are attaching to the super restrictive case of a head-on collision. If we would be able to simulate circular collisions, then we would have contributions to the final spin from the orbit. Therefore, we would be able to reduce the spin of the individual objects, and this estimate would vary. So I would say that the true result will be much wider. And this is just the signal in the 3 detectors, Hanford, Livingston, and Virgo, compared to the best fitting waveform we can get from a black hole merger in red, and the best fitting waveform from a head-on collision in green. I haven't yet said anything about model selection, which of the two things you prefer, because I'm going to do it now in the context of more events.
So you say you have access to the oscillon frequency?
The oscillation frequency determines the mass over spin ratio, basically.
Yeah, but there's no signal attached to that. I mean, you cannot, it doesn't radiate. So the fact that you have a field which is just oscillating. Yeah. But this is monopolar. This is not going to produce any gravitational wave. So you're not going to see it.
You may not see the effect of that, but you see it through the spin of the object. So that oscillation frequency determines your spin. Essentially, there is a relation between one and the other, like an equation of state. So when you estimate the spin of the things, that spin is given by the frequency. You're really measuring the frequency.
I have a very question about the prior probability of a head-on collision.
It's 0.
It's 0.
It's 0. But the philosophy here is not that one would claim that this is a head-on collision. That would be pretty stupid on our side. The philosophy here is we can get this super simple model of a head-on collision that at the end produces a remnant. And you know basically for a fact that when you do a circular merger, you're going to basically obtain the same remnant for some combination of those parameters. So you know that boson stars can actually reproduce that. So the day we are able to do the circular mergers, we basically know we're going to be able to fit this with probably with different field frequencies actually. And I haven't discussed that yet, but our model selection is going to push even more towards the boson star scenario, because the circular thing would be louder, and then assumptions about distribution of sources being uniform in the universe and things have to be preferentially far away will basically help the boson star model. I will talk about the detail in a second. But yeah, we're not claiming that this is consistent with head-on collision and therefore should be consistent with whatever can come from a less eccentric configuration. We would not say we have observed a head-on collision of two things. So there are 3 more events that we have now analyzed that are short enough that we have a chance to fit them with these very short head-on collision signals. And of course, all of them are very high mass. The first one is GW200-20. So this is part of the catalog that was recently released by LIGO and Virgo. But I have to say it has a very low significance, statistical significance below 1 in a year. So that means that the background can give you something similar more than once in a year. For the case of 1905-21, it was 1 in 500,000 years. Do you remember the IFAR of that? Thousands. I mean, orders of magnitude above. I wouldn't bet my arm on this being a true gravitational wave signal. Now, as I said, the signal is very short, and the estimate of the mass coming from black hole models is 200 solar mass. Then we have this even less reliable event, which is GW1904-26. Again, you need to have a lot of imagination to see by eye that there is a gravitational wave. But if you believe that, then this is the heaviest merger to date. And then we have my favorite weirdo as of today, which is S200-114. This is at the very least something with a clear morphology. Then you can discuss whether that's consistent with a black hole merger or what. This was not published as an event, but just as a loud trigger that appeared in the data during a specific search for high mass mergers. But the nice thing, or the interesting thing, is that this statistical significance, I mean, the rate at which the background can reproduce this is much, much shorter. It's 1 in 30 years. So it's much more significant than the other 2 events that were actually published. This is extremely challenging for our waveform models to reproduce. I will show that in a second. And with all of these things, has not yet been ruled out as a gravitational wave detection. So we're doing a lot of follow-up studies on it. I said that this thing is very, very challenging for our waveform models. And what I mean is you can predict the signal that would come from this couple of black holes via different techniques, in numerical relativity, post-Newtonian calculations, semi-analytical stuff. And at the end, you're going to end up with different models giving you predictions for the signal of a given source. And therefore, you can try to estimate your parameters with all of them. Okay. The thing is that with our 3 reference waveform models, there are no pair of models that give you consistent estimates. So rather than saying that this is definitely not an astrophysical event, it's just telling you that this is really challenging the capabilities, our capability to reproduce this type of signal. So with all of this, we said, okay, let's analyze this 3 events, and the one we initially analyzed with an enhanced catalog of boson star mergers that we now extended to almost 800 simulations. At the beginning, we had around 90. We also increased the amount of gravitational wave emission modes in there. Doesn't help very much because the new ones are very, very weak. So you preferentially radiate in this case through the 2-2 or quadrupole mode. For those that study GR, the quadrupole formula should be familiar. And the 2-0 mode in the case of head-on collisions. So let's go again through the results. I already showed 1905-21, both black hole mergers and Procastar mergers with the data quite similarly. For the weirdo that I said that is just a trigger for now, you can see actually differences, noticeable differences already by eye between the 2 models. So that means that one of the 2 at least is not working very well. Maybe the both of them. And then for GW200-20, and not even including the other event, you can also see very, very large differences at the level at the visible level. This is not necessarily bad. I mean, this could imply just that the signal is so weak that the differences between these models are just not important enough or high enough to be detected.
Sorry,
yeah.
Maybe I missed it. The BGH here is what?
BGH is red.
Right, no, but which calculation?
NR surrogate. So for those that do not know these details, one of the waveform models we use is called numerical relativity surrogate. And the advantage of this model is that it's just an interpolation through numerical relativity simulations. So it includes all the phenomenology you can find in those simulations, precession, higher multiples. So within its domain of validity is a more reliable thing you have in principle. So model selection, remember, when I'm comparing data to 2 different models, I need to decide which of the 2 is more preferred statistically, or which is more likely given the data. So this is basically the seat that I was showing in the denominator of my Bayesian inference thing for black hole merger model versus Procastar merger, and then you can translate that into a relative probability. So relative probability of one model with respect to the other. For 1905-21, which is the most significant signal, we obtain a preference of 3 to 1, nothing too nice or nothing too spectacular, but it's in favor of the Procastar merger scenario. This 1904-26 is completely rejected as a boson-star merger. The 200 to 20 is not very strongly rejected. It's only a 1 to 20 thing. And for this weird trigger, actually, there is a stronger preference for the boson-star merger scenario. But I want to go back to the thing of the distance. So as I said, for this, when we compare to the boson-star model, because it's head-on, we infer a very short distance. And this actually punishes this model with respect to the black hole merger model, because that circular black hole merger model predicts louder signals. Therefore, you can put them really farther away, 5.3 gigaparsecs versus 0.5, so 10 times farther away. And when you do this type of analysis, one of the things you fold in your priors is your assumption of how things distribute in the universe. So if you believe that the universe is isotropic and homogeneous and so on and so forth, you would say, okay, my sources should distribute in a uniform and a homogeneous way. So your analysis is going to prefer stuff that you can put farther away where it's more likely to find sources with a factor of distance squared, more or less, if you want. So that's going to punish our weak model. So we said, okay, just for fun and to understand whether this is really playing a role, let's try to remove that and try to impose a non-very physical prior in which the prior in distance is just flat. We don't prefer any distance over the other. And as you can guess, the preference for the boson-star model rises in all of the cases. This is not to say that that's the right assumption about how sources distribute in the universe. It's just to come back to the problem of what would happen if we could do these circular collisions, and therefore our black hole or Procastar model would predict signals as loud as the black hole one that we can put equally farther away. So this is basically a attempt to remove the effect of the intrinsic loudness. These are the boson masses we infer. I will show them all of them in a plot next. But basically, the two events that are confirmed detections and that do not strongly reject or either accept the boson-star scenario give you very similar masses, and that's quite interesting. And then for the weirdo, we get something that is quite more inconsistent. So these are the four masses plotted all together. This is our prior. So this prior is coming from our distribution of our simulations. And you can see that the posteriors nicely enough deviate from the prior. So, okay, we're actually getting some information there. It's not just prior driven. And as I said, the two events that do not actually reject the Procastar hypothesis very strongly have these consistent masses that you can actually exploit in a way. How much do I have left? 5 minutes?
Yeah, exactly.
Okay, so we'll not be talking about searches. So once you have many events, you can try to play a game in which you say, okay, what's the population behind those events? And this game has already been played with gravitational-wave observations, so you can have a family of detections that your detector is observing. You collect your estimates, for instance, for the masses, and that tells you what the actual distribution of the masses is within that black hole population responsible for the events you see. And then you can drive some conclusions, such as merger rates as a function of distance, whether there is a gap in the masses due to peri-instability supernova, or whether there is a lower mass gap for black holes. The absence of it would basically suggest the existence of primordial black holes. But you can play also a different game, which you say, well, let's say I have a population that now has a fraction or a potential fraction of boson stars in it, boson-star mergers. So you have a mixed population of black hole mergers and boson-star mergers. Then the observable you look at is the preference for each of the two models within your set of observations. And then you model this population as a compact merger population with a fraction zeta of Procastars in it. So you can compute the probability of the data for a given true fraction of Procastar mergers in the universe. And you can compute that, and well, I show many curves here. The one I would say is the not even realistic, but the less optimistic one is this one, where your fraction of Procastar mergers basically in the universe peaks at 0. This makes sense because you have 4 events. There are 2, actually 1, because we're removing the weirdo. There is one for which the boson-star merger scenario is kind of favored, but not in a very strong way. So you're going to say, okay, the most likely scenario is that the most likely fraction is 0, but this extends all the way to 1.
Sorry.
Yeah.
Is this a fraction among 90 events or among the 4?
4, actually 3. I have removed 214 here.
Or you put it back in this way.
And if you put it back, then you have a second event for which the boson star merger scenario is preferred, and then your distribution shifts to the right. The red curves correspond to the case in which we assume this unphysical prior that removes the effect of source loudness. So a extra game that you can play here, and with this I will finish, is, well, you not only have some events or 4 events, let's say, that have a given preference for one or the other scenario, they also share, or they may share, a common boson mass. And how is this relevant? Well, it's relevant because if you can attach to a single boson mass in your analysis of all of the events, you're gonna reduce the amount of parameters you use, and then your evidence is gonna shoot up. If this happens, then your potential fraction of events in the universe should increase, or within the population responsible for the events you're observing. The amount of agreement between 2 masses can be computed by what's called an overlap integral. Larger than 1 means that common source or common boson hypothesis is favored. Lower than 1 is not favored. And you can see that it's basically favored for all of the event couples, except when you fold in S200-114, because it has this mass that is just away, essentially, from 1905-21. So if you fold this into the analysis and you say, okay, now my prior for the true mass of these things is going to be that of the most relevant event here, which is 1905-21, the loudest, then your posteriors actually shift. So the most conservative of them is that in which you again remove the weird event, and you're left with the other 3. And now you see that you get a peak at around 0.4. This is not to say that this is the actual population of boson stars within these events, or so on and so forth. This is just an example of how you can fold in the mass consistencies to do this kind of study. Also, there is a caveat here, which is maybe evident for some people. That is that for the case of 1905-21 itself, I'm kind of artificially pushing it further as a boson star merger because I'm using as a prior its own measurement. So that's something that one should not really want to do. So we're working now on more agnostic approaches to. Yeah.
You just impose that the masses should be the same, but without assuming.
Yes, that's what we're doing now. And then we are sampling over that common mass, and you can actually propose several masses. So the result, the plot I'm working on now, I have a preliminary version, but I don't think it's yet okay, has here probability of n being the number of bosons I need to describe the population, and then 1, 2, 3 bosons, let's say. So I'm not going to get into the techniques we use for, or we are trying to implement now to search for these compact mergers. So I will skip directly to the conclusions and just basically give 2 messages. We're getting now in a situation where we are detecting stuff that is really challenging our capacity to interpret such stuff. On the one hand, it may be hitting the limits of our ability to produce waveforms for given sources. And on the other, when your measurements are driven by priors, you basically need to try everything that you have at hand. So some improvements that we want to do in the future is we're working on simulations for less eccentric configurations of boson star mergers. So on the one hand, more realistic, on the other hand, louder. We want to do a targeted search for those boson star mergers that can produce these final boson stars that emit pulses that could serve as a smoking gun. And as I just said, we're trying to work on really how to exploit mass consistency across events to basically, if one cannot detect any of these super nice boson star mergers, one can just build evidence across many events by stacking them. That's going to be it. Guess I surpassed the time limit. Sorry about that.
Thank you.